Hello, welcome to another module of this course, Microwave Integrated Circuits. In the previous module, we are in week 7 now. In the first module of week 7, we had covered about design using the gain circles for the unilateral case using the transducer gain as our specification for the gain. And then we had seen we had also discussed about the unilateral figure of merit to show how good the unilateral approximation was. I had also mentioned in the previous module that next we will be covering the bilateral case. That is the case when we do not make the unilateral approximation. So let us see how what we can achieve. Now, one thing I would like to state for the bilateral case is that unlike the unilateral case, there is not much design flexibility. I mean, what we can achieve mathematically is to specify the maximum gain that we can get, unlike the unilateral approximation case where we could specify a particular gain and then draw load side and source side gain circles. In the bilateral case, we cannot do that. Now, if the device unconditionally stable that is k greater than 1 and b greater than 0 or delta less than 1, then for conjugate match we have to have and gamma L should be equal to now we know what is the equation for gamma in and the equation for gamma out, and if we solve these two equations simultaneously, then the solution that we get is given like this. Where these B1, B's and C's are given by now from this now if we substitute these values into the gain equation, then the value of gain, we call the gain equation for the non-unilateral case, that is when we do not make that is when S12 is not equal to 0. I am not repeating that equation, but if we substitute these values of gamma S and gamma ML in that equation, what we get is actually the maximum possible gain, maximum possible value of GT for the bilateral case. And that value of GT, that maximum value of GT that we get is given by now we can show, we have already talked about GP, that is the power gain or operating power gain, and GA, This is the available power gain. Now we can show that GT max will be equal to GP max, which is equal to GA max. Now this can also be simplified like this. Just dividing the numerator and denominator by k plus square root of k square minus 1, what we will get is this. Now this S21 upon S12 is equal to any of the values, that is, this is also equal to Y21 upon Y12. You can verify that from the conversion formulas for Z between S and Z parameters. Now, so we saw that this is the case for the unconditionally stable case. Now, for the unconditionally stable case, this GT max that we just found out, which is equal to GA max. Now, this is actually a figure of merit. Actually, this is actually a specification given in the data sheets of the RF devices that you suppose you buy from the market. Then this GA max will be a specification that is given with the device. This is also known by the term MAG, that is maximum available gain. Now we see that K equal to 1 defines the boundary between unconditionally stable and potentially unstable. So we see that at K equal to 1, by the way, this K is the stability factor that we had studied above previously, and that is also related to this GT. So if we just come back to the previous slide, now this GT max is related to K. K comes into this equation, and this value of K is the same value. This K is the same value as the K that we discussed while discussing stability. Now at K equal to 1, this GT max becomes what? GT max becomes simply equal to S21 upon S12. That's it. So this is that at the stability boundary, this is the value of GT. And in fact, this is also used as a this is also a figure of merit, and it's known by the term MSG. MSG, which means MSG, which is equal to S21 upon S12, and this is known as the maximum stable gain. Now for K lesser than 1, there is that is for the potentially unstable case, a simultaneous match doesn't exist. So at K equal to 1, we have a match is possible, and the gain at that value is given by this. For K lesser than 1, that is, now we are in the potentially unstable region, a simultaneous match doesn't exist. It is not possible to find a matching network which can satisfy the two equations that I described before. However, for the K greater than 1, now for unconditional stability we saw we need K greater than 1, and delta modulus lesser than 1. If both these two conditions are not satisfied, then it is potentially unstable. For a particular case, when delta, when if I take another slide, so for k greater than 1 and mod delta greater than 1, this is also potentially unstable. For this particular case also, it is possible to find a value of gamma ms and gamma ml, and these values are the same that we obtained for the unconditionally stable case. Now, of course, since this is now potentially unstable, instead of GT max, we will have a GT min, that is a minimum value of the transducer power gain, and that value is given by instead of the minus, it is now plus here. And if we go to the slides on the monitor for a moment, this is the typical GT versus frequency curve for a standard RF device. We see that for high frequencies, it is unconditionally stable, and that's why this MAG exists. But for lower frequencies, this MSG is the specification at the stability boundary that is given. This is often a graph that is supplied with RF devices, and we see that as lower frequencies, the device is less stable as compared to higher frequencies, and for a particular value of f called f max, the gain, the value of GT or GT max becomes 1. That is, beyond f max, it no longer gives any usable gain, and this f max, MSG, and MAG are often the parameters that are supplied in the data sheets of many RF devices. Now, so we have discussed how to design using the transducer power gain for the unilateral case, and also how to find out the maximum available gain or the maximum stable gain for the bilateral case, depending on whether we are in the unconditionally stable or in the potentially unstable regions of the RF device. Now, but then we see that if we have the bilateral case, then we cannot we cannot set a particular gain for the particular value for the transducer gain. So, to get around this problem, we use the other two gain definitions that we have used, that is the operating power gain and the available power gain for designing RF circuits. So, let us see how to do using how to design using these two power gains. Now, if you fix a particular value of the operating power gain, then the locus on gamma L, recall that in power gain, operating power gain GP is a function of gamma L, the load reflection coefficient. Then the locus of gamma L for a constant value of GP, it can be shown, the derivation is there in the book by Gonzalez. It can be shown that the locus is like this, where this Cp is given by this is the value of the Cp, that is the center of this circle, and Rp, the radius of this circle, and the center of this output. This recall is an output stability circle because it is a function of gamma L. The center of the output stability circle, the center of the constant Gp circle, and the point gamma L are equal to 0, are collinear. The other thing is when gamma L is equal to gamma ml, this is the solution obtained for the bilateral case of the transducer power gain, then Gp max is equal to Gt max. So these operating power circles are like this. This blue circle is our Smith chart, and these red circles are the operating power circles. As we see that all the centers of all these circles are collinear, because Cp is given by this expression, and the value of this C2 is given as S22 minus delta S11 star. This is a vector quantity, the others are scalar quantities, and therefore all the centers of all the operating gain circles will lie on a straight line. This small Gp, I didn't mention what is the definition, is the small Gp is defined as the actual power gain divided by S21 square. So this is the normalized, so this small Gp is the normalized power gain or the normalized operating power gain. So, how to design using these operating power circles? So for a given, suppose this is our Smith chart, and say the power gain circles that we obtain are like this. So the steps to design are: first, for a given Gp, draw the operating power gain circle. Then since this is the gamma L plane, select the desired value of gamma L. So suppose this is the gamma, this is the gain circle that you are interested in. So select a point gamma L, and then that is the value of gamma L that you choose for your design. And if you want to make the transducer power gain equal to the operating power gain, that is for making Gt equal to Gp, so you chose the value of gamma L here. This is the value of gamma L. Say this is the gain circle. Say this is the, say you need a Gp of 10 dB, and say this is the 10 dB gain circle. Then you choose a point on the circle that gives you the value of gamma L. From here you get gamma L. Once you get gamma L, you can calculate gamma in, and then gamma S will be equal to gamma in conjugate. This will also ensure that Gt is equal to Gp. Now for potentially unstable case, let's see how to do the design for potentially unstable case. For the potentially unstable case, say this is your unit circle and this is your stability circle. So this will be the output stability circle, okay, and you choose so same as the previous case, you choose a particular gain circle, select the value of gamma L, ensure that gamma L that you choose lies in the stable region, and then once you choose gamma L, you can find out gamma in, and from gamma in you can find out gamma S. Now one important factor that you have to take into account when you do this is that you have to draw the input stability circles as well, because if you choose, as I said, you have to choose gamma S is equal to gamma in conjugate, but then this gamma S itself should lie in the stable region of the input stability circle. So that you can do by drawing the input stability circles and then seeing whether the gamma S that you have obtained using this equation indeed lies in the stable region. If it lies in the stable region, then that is fine. Otherwise, you need to choose a different value of gamma L and repeat this whole process again. Operating power gain circle based designs are can be used for certain types of amplifiers like power amplifier, where the load where the input impedance is fixed but the load impedance can be varied. Then there are other amplifiers like the low noise amplifier where the output is fixed but the input can be varied. So for such type of amplifiers, as I had already mentioned before, you might want to use the available gain circles for design. So let us see what are the available power gain circles. So available power gain circles are very analogous to the operating power gain circles. Let me choose a different. So they are very analogous to the discussion that we had for operating power circles, that is the locus of gamma S for a constant available power gain will be given like this, where this is the equation for the available power gain, and if we go to the slides on the monitor, just like the operating power gain circles, the center of all the available power gain circles will be collinear. This is of course the gamma S plane. For the operating power circles, it was the gamma L plane. And so the way to select, so the way to design is that suppose this is the 10 dB available power gain line and you need a gain of 10 dB, then choose a point on this circle, this red circle, that lies within the Smith chart. This is of course, we are assuming this is the unconditionally stable case. You choose a value of gamma S and then find out what is the value of gamma out, just like we found out what is the value of gamma in for the operating power gain circle case. Once you find out gamma out, I beg your pardon, you set gamma L equal to gamma out conjugate, and this is the value of gamma L. When you do this, the GT will be equal to GA. For the potentially unstable case, you draw the available power gain circles, you also draw the input stability circle. Select a point on these available power gain circle that lies in the stable region. Once you select a point, say that a certain value of gamma S, find out the value of gamma out, and then set your gamma L is equal to gamma out conjugate. Once you do that, you now draw the output stability circle where we are in the gamma L plane, and see whether this gamma L that you just obtained using this equation really lies in the stable region. If it lies in the stable region, then fine. If it doesn't lie in the stable region, then you need to find another value of gamma S and repeat this process till the time that gamma L, both gamma S and gamma L are in the stable regions of the input and output stability circles respectively. So in summary, in this lecture we covered the bilateral cases. In the previous module we had only covered the unilateral transducer gain case. For bilateral matching, for the bilateral for finding out if we consider only the transducer gain, then we saw that a bilateral design is mathematically very difficult, and what we can obtain is the maximum, specify the input and output reflection coefficients for obtaining the maximum value of GT. For the available power gains and the operating power gain, we saw that we can do a design even for the bilateral case. Of course, for the available power gain circles, the load reflection coefficient is always the conjugate of the output reflection coefficient, and for the operating power gain circles, the source reflection coefficient is the conjugate of the input reflection coefficient. So, and as I said before, the available power gain circle based design is used for those amplifiers where the output impedance is fixed, but the input impedance can be varied, and the operating power gain circles are used for design of those amplifiers where the input reflection coefficient is fixed, but the output reflection coefficient can be varied. In the next lecture, we shall be covering another important aspect of amplifier design, which is noise. So that is what we will be doing in the next lecture, next module. Thank you.